All right, so let me explain this beautiful article from Google Brain about reasoning, which is called Least to Most Prompting Enables Complex Reasoning in Large Language Models. So what is the motivation behind this paper? Chain of thought prompting has demonstrated remarkable performance on various natural language reasoning tasks, as I've explained this article in my previous lectures. However, it tends to perform poorly on tasks which requires solving problems harder than the exemplars shown in the prompts. Something like, for example, out of distribution generalization task that we want to handle a complex problem that has not been trained before. To overcome this challenge of easy to hard generalization, we propose Google Brain, they propose this least to most prompting approach. So there is a difference between human and machine. So given a new task, humans usually can learn to accomplish it from only a few demonstration examples. Just like few-shot learning, but more advanced than that. While machine learning requires a large amount of labeled data for model training. Traditional supervised learning, it's very data hungry, it's very bad. Humans can clearly explain the underlying rationale for their predictions or decisions, while machine learning is essentially a black box. So it's a black box, it's not explainable, all of that. Humans can solve problems more difficult than they have seen before, while for machine learning, examples in training and testing are typically the same level of difficulty. So for a machine, it doesn't matter if you're a training mode, developing mode, test mode, doesn't matter. And so they draw inspiration from educational psychology. It's a field very interesting. It's related to studying teaching. Knowledge tracing is another topic in machine learning that people want to learn how to teach students. For example, e-learning and those stuff. So it is also related to this as well. So development, motivation, and learning psychology is related to educational psychology. On the other hand, teaching, knowledge, setting for learning, general teaching strategies, and also it is related to this continual learning, lifelong learning. So you see that these words that you see in that article are like this: most to least, least to most prompting. So you see why this is a motivation for Google Brain. So we decompose question into sub-questions. This is a major paradigm in many of the articles that I've explained and my playlist for question answering, as well as the current playlist for reasoning. So it takes Amy 4 minutes to climb to the top of the slide. It takes her 1 minute to slide down. The water slides closes in 15 minutes. How many times can she slide before it closes? To solve how many times can she slide before it closes, we need to first solve how long does each trip take. So this is one stage. And then after that, in the second stage, where we want to sequentially solve the problem, we get the same thing again, but we say how long does each trip take? Because this comes here. And so each trip takes 5 minutes. So we take advantage of that. We append it. And then we create the context. Again, we use the language model to see that, for example, the water slide closes in 15 minutes. Each trip takes 5 minutes. So we are teaching the machine how to learn. We are like a student that you are teaching step by step of, for example, you're teaching mathematics to elementary students. So at each step, you should know what is the prerequisite for the next stage. Then what is the prerequisite for the next stage? And so on until they understand all the steps during this pipeline of teaching and learning. So least-to-most prompting teaches language models how to solve a complex problem by decomposing it into a series of simpler sub-problems. So first decomposition, the prompt in this stage contains constant examples that demonstrate the decomposition, followed by the specific question to be decomposed. And then we have sub-problem solving. The prompt in this stage consists of 3 parts: constant examples demonstrating how sub-problems are solved, and then a potentially empty list of previously answered sub-questions and generated solutions, and then the question to be answered next. So we asked the language model to sequentially solve the sub-problems from the problem decomposition stage. The original problem is appended as the final sub-problem. The solving starts from passing to the language model a prompt that consists of examples that illustrate how problems are solved. How long does each trip take? We then take the answer generated by the language model. Each trip takes 5 minutes. And construct the next prompt by appending the generated answer to the previous prompt, followed by the next sub-problem, which happens to be the original problem in the example. The new prompt is then passed back to the language model, which turns the final answer. So this is problem decomposition. We have a question: how much older is Rena than Pam currently? And the answer is, since Rena will be 5 years older than Pam in 10 years, she must be 5 years older than Pam now as well. So the answer is 5. You see all of these stages for concluding the final decision, which is 5. How old is Pam now? If Pam is currently twice as young as Rena, that means Rena is currently twice as old as Pam is. So if P stands for Pam's age now and R stands for Rena's age, then we know that R is 2 times P. And since Rena is 5 years old, we know that. So we can test these things, for example, in this website, po.com. You can ask such questions. And of course, you cannot teach them because it is already fixed. The weights are already fixed in 2011. But you can see if it can do some kind of reasoning as well. So there are limitations. Decomposition prompts typically don't generalize well across different domains. For instance, a prompt that demonstrates decomposing math word problems isn't effective for teaching large language models to break down common sense reasoning problems, such as did Aristotle use a laptop? A new prompt must be designed. So for each one, a new prompt model should be designed for each task. So this is the limitation of that. So we need a kind of transfer learning or domain adaptation such that it could handle, for example, fact detection, event detection, and other tasks such as episodic memory or associate memory or different tasks. We want to see how we can unify all of them with just one prompting model.